So the Cartesian plane...
Gee, that's a great title. I'm just going to say up front, I love that. I feel like it's a science fiction movie. Cartesian.
Because you think about an aeroplane, yeah.
Yeah. Well, yeah, and it's also something spectacular about it.
There is actually something spectacular about it. To understand this, you'll need to know about basic algebra and basic exponential notation. Now, I'm really fascinated by things like the wheel that were invented that seem so obvious once you've got it, but took a long while for people to invent, and people like the Incas never came up with it, and they built Machu Picchu without it. You know, can you imagine the effort? Another example of the wheel is the umbrella, which was actually existed as a parasol in ancient Egypt, and in ancient China they realised you could keep the rain off. It didn't realise that in the West until sort of the 1700s. All that time people were getting wet, but they still had parasols because no one thought, this could keep the rain off as well.
Fascinating, isn't it? Like that, how your current way of thinking can lock you in.
Can lock you in. Yeah. Paperclip. The ancient Egyptians had wire and they had paper, but it wasn't actually until 1899 that someone thought if you bend the wire the right way, then you can keep paper together.
Right, okay.
So a similar thing happened with the number line. Now, number lines have been around forever. Every time someone measured something by tying knots in a string to get the distance, you effectively had a number line. The Indians in the first millennium AD came up with the brilliant idea of putting a zero and then negative numbers into it, which turned out useful for all sorts of things. But it wasn't until René Descartes, who's the philosopher who gave us, I think, therefore I am, and he did in so many ways, who lived between 1596 and 1690, came up with the idea of turning this number line into the Cartesian plane, which is where the number comes from, René Descartes, Cartesian. And the thing is, historically, up until then, in just about every way, Europe lagged behind behind India, behind the Islamic world, behind China and the Orient in technological development. They were coming out of the Dark Ages. The discovery of algebra, when it came in from the Islamic world, helped mathematics to move along. Discovery of different ways of lending money and the triangular sails, which let you sail against the wind, helped. They were starting to expand, starting to move properly, starting to rediscover ancient Greek things, but technologically they were definitely behind until René Descartes came up with the idea of let's take another number line and put it around at right angles like that, which seems like a fairly simple thing to do, but that absolutely changed everything.
Wow, just that one thing.
Just that one move, and what he did with it was totally revolutionary, and that's what really allowed every scientific advance since then.
Is that incredible?
To happen, yeah. So what this meant, effectively, the other thing he did was he gave the allocated letters, algebraic letters, to each of those axes.
This is the X and Y axis.
This is the X and Y axis. So say, well, let's have the horizontal one, we'll call that X, we'll call it vertical. We'd call them anything, in fact, do different things, but with X and Y. But what it meant is you can draw up an algebraic equation and visualize it, was what was really happened here. So it enabled a complete shift in thinking. So if we take a simple one, we say X equals Y. So if we say X is at point 1, then Y has to equal the same point. So that point is going to be there. The point where X equals 1 and Y equals 1. We call the point 1, 1. We've got a point for it. If X is 4, Y is 4, it's going to be up there. X is minus 1, 1. And in fact, what that draws is a line. Any point where X equals Y is going to be on the line. Any point where X doesn't equal Y is not going to be on the line.
That's so helpful for me to visualize, see the visual expression of that.
Yeah, so you just got an equation, and suddenly you've got a drawing that came out of it. Algebra and geometry suddenly work together, and everything else in terms of calculation starts to become possible from there. So if we were to change that equation and say Y equals X plus 4, we just elevate the line by 4 points, because at each point we get to x, we just add 4 on. So when x is 0, y is going to be at 4, and so on. When x is 1, y is going to be at 5, and so on. But otherwise, we haven't changed the slope. Where x is minus, where y is minus 1, we're going to drop it down, and so on. If we multiply x by something, say we multiply it by minus 3, then it's going to end up looking like this. So for each
the
time...
other side then is negative, is it?
Yeah.
Going to the left?
Yeah,
Right.
to the left and to the bottom is negative. So we've got a
Okay.
whole 0 and going in every direction. And the slope of that line, so for every time you move forward 1 space with x, you're going to move downward 3 spaces with y.
Okay.
So that kind of looked at this when we looked at the slope of a line, but the minus 3 is actually going to tell you what the slope of that line is in this instance.
Okay.
If we do something else with x, if we square it, it was also Descartes who came up with the idea of using those subscripts, that little 2 there, in order to express working as a power. People had never really thought about doing that until they could draw it, which is one of the sort of revolutionary
What a
ideas.
brain. What a brain the guy must have.
Yeah, well, he wasn't kidding when he said, I think, therefore I am.
Yeah.
So it draws up a parabola, which looks like that. So when you x equals 1, y equals 1, when x equals 2, y equals 4, when x equals 3, y equals 9, and so on. And when x equals minus 2, because multiply d negative, you get a positive, y is also equal to 4, and so on. So that's the points that equals fit on the line. When x equals minus 1, draws up a diagram of a thing called a hyperbola.
Oh, I've seen that pattern somewhere. Anyway, yeah.
Yeah, so you can kind of see as x gets bigger and bigger to the right, then y gets smaller and smaller, but it never quite gets to nothing.
Is that exponential? Or is that different?
Exponential is different. No,
Okay.
no, but
Let's not muddy the waters then.
Let's not muddy the waters, but similar thing. But if we zoom right in there, and we don't just change what x is doing, but we change what y is doing.
Yeah.
So if x squared plus y squared equals 1, draws a circle around there.
Okay.
In fact, what's
I
called
really
a
like this.
unit circle. And if x squared on a squared plus y squared on b squared equals 1, that draws an ellipse. Why that particular thing was revolutionary is that planetary orbits also form ellipses, and a lot of what was important in mathematics in the early days was astronomy, because you used it for navigation, and if you got this slightly wrong, if you could navigate better, you were safer, you had more efficient trade, you had so navigation was incredibly important. That and so many other things came out of the Cartesian plane. Thank you for watching.
Good on you, Renae.